Next speaker, Ravi Ilango, who is data science director at Stealth Model Startup. And Ravi will tell us about using transformers in natural language processing.
Sure.
Ravi, microphone is yours. Please go ahead.
Great. Thank you for the opportunity to talk to you guys. Hope you are having a great day. So this exercise will take probably anywhere between 30 to 45 minutes. And I do have a presentation to start with. All right. Can you see my screen?
Yeah, we see it perfectly.
Okay, great. Again, good morning or good evening. I don't know what time zone you're in. I just want to spend the next 30 minutes or something talking about NLP in general and how do we use this latest and greatest technology called transformers in NLP world, in AI NLP. NLP stands for natural language processing. That's what it is. I just want to get a show of hands. How many of you are practicing data scientists? How familiar are you with natural language processing, Python, those kind of things? I don't know how we can talk here, but any idea? I can see 6 or 7 people here.
Yeah, actually, we have 10 people here in Zoom, but most of the people are on the broadcasting link.
Okay.
And they do not chat a lot. They are watching us on Facebook and YouTube.
Excellent. Excellent.
If there would be any questions or comments from them, I will pass it to you. Also, we have Telegram group, and if there appears anything, I will also pass.
Excellent. Okay, so this is my bio. I currently work in a stealth startup. It's kind of not a stealth startup anymore. We are reinventing or trying to disrupt the construction industry. Right now, there is one company which has been public called Procure. They're also providing the construction software for construction industry, and we are also working in that same space. And as part of that, we do a lot of NLP-based work, video-based analysis, two-dimensional, all kinds of things we do. So before that, I was working in 3 other startups in the last 4 years. And before the startup world, I was at Apple for 10 plus years and many other companies. This is my profile. Okay. All right. So let's just get our feet wet on what is this AI is all about. I don't want to go through this standard slides, but I'll quickly spend some time to get the context, right? So AI is popular everywhere, right? Wherever you turn around, you see AI around there. One great example is self-driving cars. 10 years ago, I never thought self-driving cars are going to make it, but now you see it everywhere. I drive around in Bay Area, and I can see a lot of the Google test self-driving car nicely going around, stopping, taking a left turn, right in front of me, which is kind of cool. So we see AI all over the place, all around us. It's just happening. 10, 15 years ago, it's not that the case. Right now it is. So how is this all possible? So predominantly we use machine learning, which is a subfield of computer science, where machines can learn to perform certain tasks without explicit programming. Typically, we do programming, we write if-then-else code, conditional stuff to do certain things based on certain events. The idea of AI is it does it by itself. You don't have to do that. You just give it input data, you tell that sample outputs, it figures out the relationship, and you can build systems around it, right? That's all it is. Machine learning basics, basically you have something called a label data, and machine learning algorithm learns from it. Label data means known input and known output. Once you have a learned model, you can use data to do the predictions and the wonderful things. Another quick example is if you know the Monday stock prices, and can we predict the Tuesday stock prices if you know all the old stock prices? This is the kind of what a supervised learning does. Okay. And quickly moving on, typically a computer vision system, right? Recognizing a face, recognizing key points in the face, all of them, how do they work? It's basically every computer, here it's a black and white image, a grayscale image. It is represented as pixels, right? It's a matrix or a set of vectors of integers. That's how it is represented, which is from 0 to 255. And we build a model which will learn from these numbers and come up with a probability distribution for the presidents, right? In this case, Lincoln has the highest probability. Then we say that, hey, this picture is nothing but Lincoln. The idea here is the computer vision, which is in the pixel form, is represented as a vectors, and then you build a model around it, trying to see the relationship and come up with an answer, right? So coming quickly to an NLP or a natural language processing, language is all about words, right? It's letters, forms, words, and sentences. That's what it is. So we don't have numbers anywhere, right? So the first fundamental thing in NLP is what we call is word vectors or embeddings. That's what we call it. It's basically what you take. You take any word and project them into a n-dimensional space. So in this case, it is a three-dimensional space. We have three words: car, dog, and cat. They're projected. So it has got the coordinates basically tell it where they are. By looking at the words, how close they are, it means something. So these are two animals. They're kind of closer to each other as opposed to car. This is kind of a representation of words into vectors, which is a fundamental of any NLP processing. The first thing what we do in NLP processing is take a paragraph or a big corpus, convert that into sentences. From sentences, we convert that into words, and every word is given this kind of a vector. Either you train it to come up with this kind of vectors, which makes sense, how far or close they are, or there are pre-trained models where the word embedding or word vectors are available. I just want to bring that up here to you. So it's kind of important. Now let's come back to NLP every day, right? Google Translate, right? Up to 500 million people use every day. Let's use NLP. Chatbots, you know it. Alexa, email assistant. All these are all day-to-day use of NLP. But in the business world, mostly what I have seen is text classification and any text analysis techniques. That's pretty much what we text summarization. Only those kind of things are used in the business world. Everything else is part of a product offered by bigger companies, right? That's how NLP is being used. Data produced, production rate is huge. I won't go through this number. This is old data. So we have data produced all over the place, and we should have good tools to analyze them and make use of them. That NLP is one of the good tools. The text data, if you think about it, out of 80% of the data in organization are in the text format. They are in chats, emails, most important. Then they're in documents, a lot of PDF documents, scanned documents, and other things. The company which I'm working on, we are working with PDF documents and drawings. They're all in different formats. Different countries use different kind of style of drawings and everything. The text is there all over the place, and it's our job to use techniques like OCR and what else? A lot of text NLP libraries to analyze, gather the text, analyze it, and make use of it. Okay, so this is all not easy problem. This is pretty tough problems. So why is it tough problem? Let me quickly jump to that. So look at these sentences. I enjoy working in a bank. I enjoy working near a river bank. The bank is completely different in these two, right? If you just take a word vector of a bank alone, it's completely different in these two contexts, right? This is the river bank, and this is actually a commercial bank. So this is important because it's not a straightforward conversion of information, conversion of the words and sentences into some kind of logic or a vectorial representation. It's although the context also matters, right? That's important. So another thing is I made her duck, right? That's a very straightforward English sentence, but it also means that I made her duck, which you lower your head. It's another meaning of it. So I cooked the waterfall for her benefit, right? I made a duck meal, right? That's important. I cooked the waterfowl or duck belonging to her. So there are a lot of different ways you can use it. This is English sentence, right? So that's why it's complex. Deriving meaningful information from text data and actually use it for commercial purpose. That's the key, right? Google Translate does a great job, and Google searches do a good job. But if they err out a little bit, what is the commercial implication? Probably nothing, right? We won't use Google. That's the only thing. But in the area which I work on, if I do a mistake and people do take actions automatically and it costs them money, we'll get sued, right? There is a commercial implication. So you have to be very careful in using these kind of tools. All right, I'll just keep going. This is just to illustrate to you how, even though NLP language, humans do a good job in looking at the sentences and making sense out of it. For computers to do it, it's tough for it to do it because it's very context sensitive. Okay, it needs to learn a lot of things. Okay, I'll just keep going. Here it is. Here's an interesting one. Now, not only we're using languages, we are using emojis, hashtags, and memes, names, right? All kinds of things we are using in the language, and this becomes part of the chat or any conversation people are having nowadays, which means we have to parse this information too and make sense out of it. So NLP is getting interesting as we go along. Okay. So if you want to be NLP, there are scientists, which some of you probably are. Some of the tools you should know how to use it, right? Python, sklearn toolkit, Spacey, Gensim, NLTK, transformers, PyTorch, and TensorFlow are all deep learning networks. I think one of the exercises what we'll do today, we'll use PyTorch, transformers, and Python. That's what we'll use. But these are the kind of a cool tools to know when you're working in NLP. I haven't done core NLP. I have not done NLTK except for a few things here and there, not even PyText, but all the other things I have played around with. Okay. All right, let's keep going. This is a typical a DS or data science model implementation. You identify an opportunity, you build a data pipeline, build a training data set, then you tune the model, build an inference pipeline, which means the predictions are based on the model. Then you use it in a production environment, in whatever business process you want. Then you assess the performance. You keep doing this as you start using it. Okay, this is the generic pipeline. If I'm going too fast, feel free to stop me and ask questions, right? I want to get to the real thing about transformers quickly because we have only 45 minutes given to me. So let's come to, I'm going to make a leap of faith assumption that some of you or most of you are familiar with deep learning networks. Even if you're not familiar, don't worry about it. We'll just go through conceptually try and understand what's going on, right? There's something called, before we come into this transformers, there's something called recurrent neural network. That was the technique used in the deep learning network. It's a deep learning frameworks for our learning from temporal data. When I say temporal data, data has just got a sequence, which is a time series, right? You have got a stock data coming in every 50 minutes. It's a time series data. Gene sequence, it's a sentence, it's a sequence. And stock prices, of course, it's a time series data. Sentences, of course, it's time series because the first sentence comes, second sentence, third sentence, they're all related, right? These are all sequences. Even within the sentences, the words are temporal data. It has got a sequence, 1, 2, 3, 4. So in a traditional machine learning network, you have an input, which is set of vector, you have an output. That's how it works, right? When you're using a temporal data, you not only have input, you work with n number of inputs, and you start predicting n plus 1 output, some other output or some other kind of output you do based on the 10 different inputs, right? 10 sequence inputs. That is what sequence learning is all about. So RNN networks were supposed to work not only with one set of data, it will work with a series of data, right? That's how it was set up. The idea is very simple. This is explained better. These are the different temporal data, right? This is probably at time t minus 1, t minus 2, t minus 3. That's how you want to look at it. You can say it. So these are different set of data. It goes through the same engine or machine learning engine, which actually kind of uses a lot of weights to extract some information out of it, and it produces an output. right? This is a traditional machine learning network. In a recurrent network, what it does is it not only produces output, it also takes the results of the previous processing as an input. So in the sense, when if we are using time series data of chunks of 10 elements each, the 10th element will actually use the input from 9th element, 8th element, 7th element, everything together to produce output. In this case, actually, it is actually producing the result, which is based on all the t minus 10 elements. I don't know whether it makes sense or not. Another easy way to think about is as simplest RNN model or a time series model is moving average. What do you do, right? Moving average is a very simple technique people use. It's very powerful. Moving average is nothing but average of the last 3 elements, right? 3-point moving average or 5 elements, right? And it gives a good, nice, smooth curve, right? So it's very similar to that. Moving average is the mean of the last 3 elements. Instead of taking the mean, we extract information using deep learning and use it again for producing the results. That's the way to think about it in terms of RNN. So it worked well. This is kind of an interesting thing. If you take the movie was bad and long, right? That's a sentence, right? You convert that into a set of vectors. These are all word vectors, right? Or embeddings, you want to call it. And all these are used together at the same time, right? And if you see the end of sentence, it actually takes the output of all the previous words, right? And similarly, long takes output of all previous words, and everything together produces a result, positive or negative. That's what we are doing. It's a sentiment analysis is a kind of application. So RNN is good in working this way. LSTM is another form of RNN, which is more powerful than RNN. So let's leave it as it is. The drawback with these tools is it did a good job in actually using the temporal data prediction. It does it. It did a good job, but you cannot process lots and lots of document because the parallelizing is kind of difficult because you cannot parallelize this because this depends on all these at the same time. So you have to take everything together, and that has to be done as a single unit, right? You cannot parallelize all these activities. So which means that the computing power required is a lot. You cannot do a lot of parallelizing. And it had limitations in terms of memory, right? When this word is getting processed, most of the information, the sequence, long sequence, it could get lost. LSTM somewhat addresses it, but it's possible that things could get lost because due to certain techniques called vanishing gradients, those kind of things. So without getting into details, but this LSTMs and RNNs serve the purpose, but when it comes to training large chunks of data, it had its own limitations. That's where transformers comes in. That's the greatest and latest stuff. Okay, we will do one exercise on LSTM and as well as transformers if time permits. Okay, this is the kind of interesting thing about LSTM. People are quite happy with space. Oh, this is just I took out the name of the president as blank new president, right? So LSTM needs to figure out what needs to be here, right? So it needs to use there because there is derived from the word people, right? Because it's plural, this has to be plural. It can be her or his, right? That's the key. So that's where the LSTMs and RNNs play a good role. LSTM in this case remembers the nearby letter words, and as well as it remembers letters from distance so that it makes the right call on what word to use, right? Which is kind of cool. Okay, all right. So I have a lab here. How are we doing on the time? We'll come to this lab, the LSTM based lab later. We'll do the transformers first, then we'll come to this if you have the time. Okay. You have any questions here? Sorry. Okay, great. So let's go and keep going here. I want to introduce you to one more sequence to sequence learning, which is again RNN or LSTM based approach. So here what happens is This is a language translation model, right? So it takes a 3-word as an input, sentence as an input, and produces a word, a sentence which is comprises of 4 words in a different language, right? That's what it is doing. The way it works is these things, as you can imagine, these are all either LSTM or RNN boxes. This is the first word, second word, third word. They all get processed. Once the end of sentence is arrived at, it starts producing an output in the different domain. In this case, it would be English to French or French to English. It first produces the first word in the French based on this whole sentence. That then the first word plus the whole sentence information is passed on to the next predictor, and it produces a second word and so on. So at the end, it produces a complete sentence, which is expected to represent the input sentence in a different domain, right? That's what it's trying to do. This is again an example of where you are using LSTM or RNN for processing, for doing the translation, right? This is a sequence model translation. And let's see how it works. It's the same thing here. If you see here, this is the French word. I'm not French, but I can just chat, whatever it is. So it's Nair. This is the French sentence. It goes through the embedding process. It goes through the same thing, the network, what I told you. It's called an encoder network. And once the end of sentence is done, the whole context is passed on to the decoder, and it produces the starts producing the results in English, right? The cat is black, right? That's what it's doing, right? Now, this as I said, it has this whole network is based on either RNN or LSTM technology, which is kind of inefficient for processing lots of data. That comes the attention network, right? The attention network, what it does is, from a logically, if you think about it, it is taking all these words and only the output from the last word is given here, right? Instead of doing that, why don't we give all these words together as an input, right? That will be more meaningful, right? That's the idea here. So if you see here, all this processing is done, the context is provided. In addition to that, you're also taking the encoder outputs directly and providing all the outputs to the decoder. So this decoder right now, from the standpoint, it not only gets the output from the last word, it gets the hidden information or outputs from all the words at the same time. So it has more information to process with. And that this is kind of called attention network at a high level, which is produces better accuracy. And also all these activities, lots of activities can be actually parallelized. So it's faster too, right? It's not. Let's come to the parallelizing later. That's a transformer network. But just understand the attention network basically gives you gives information for all the input words to the decoder, right? That's what it is doing. And attention transformers actually use the attention-based approach, right? I won't spend too much time on the transformers. We'll do a cool exercise so they can have some fun. So if you want, you can the link gives you access to the paper. Go and read the paper, understand what it's doing. I will not even bother explaining this in this context at this point. All you need to know is it is doing something like attention of all the different inputs. All the words are taken into account. It pays attention to all the words and relative and the interactions between the words, like this. For example, this is the input, and it does a self-attention, which means every word is trying to figure out how the other words in the sequence are related to it. And wherever it finds something more important, it keeps track of it. For example, the animal, that is important, the street, the cross, the I don't know why that's important, but it keeps track of where all these words can be of use, right? So the thicker the word, it means it gives high marks in terms of attention. So it has, from a relation perspective, it gets the most information about the sequence. That's the self-attention, and that's again used into the deep learning model using matrix multiplication, softmax, scaling, and other things. And you use multiple layers, so they start extracting different kind of information on top of it. And you start using that's a multi-head attention. Once you have it, then you can use the decoder to output basically a probability distribution of what you want to see, right? That's what it is. So I won't go through all those things, but you guys are welcome to go through these links. These are pretty useful links, which will try to help you in understanding more about how this math behind the whole thing works. And if you have any questions, feel free to contact me also. And I like this illustration, which is kind of cool. Hope this works. Let's see. Where is it? This kind of tells you what's going on here. See, encoding, this self-attention is happening. Like every word is trying to understand what it's doing. Then again, with the derived information, the safe self-attention is happening across. Then the decoding takes all of these and provides it, then start providing the output, right? This is the next word. Again, all of these are coming in as an input. It provides an output. I like this. This kind of tells you the way the attention is being done. Let's go through this again once. This is the input. The first thing is it'll do a self-attention among the words. So it gathers information which is important to each other. Then whatever information gathered is the next layer. It does the same thing, it repeats with further refined information. This is the final output. All these are given at the same time. See, all these things are given at the same time to produce the first output. And it happens again and again. So it gathers a complete output. So this is how the transformer-based decoding and encoding works, right? The reason for encoding is it is producing an output. It's a sequence. It doesn't have to be a sequence. It could be a simple classification too, right? Okay, so I'll stop here. Let me go back to my slide here. Illustration. Let's talk about PyTorch transformers, right? PyTorch transformers is state-of-the-art pre-trained models for natural language processing, right? The pre-trained models are BERT, GPT. There are plenty of pre-trained models available. Let's talk about what's a pre-trained model, right? It uses a technique called transfer learning. The idea here is, let's talk about pre-trained model. Pre-trained model is nothing but an example of the pre-trained model is BERT. What they have done is they have set up a transformer network and they trained it using 2.5 billion words from Wikipedia. Book corpus another 800 million words. Batch size, training time took it's 40 epochs. They did it and they took it around 4 days to do it in a pretty powerful machine, right? 4 days to do it. And you and me cannot do this because we don't have access to these machines, right? This is what they have done. They kept all these pre-trained models available for you so that you can just take it and fine-tune a little bit to your own application and then use it. That's the idea of pre-trained models and as well as using transfer learning, okay? And this is how the basic raw pre-trained model works. They actually pre-train using missing predicting the next sentence, and as well as missing words. They mask. They take the way this pre-training is done is they take these big chunks of data, they mask certain words, and let the model predict those missed words, and they correct it. That's how the loss function is defined, and it gets trained to predict the masked words better and better. That's how it's trained. That's one way to do it. The other one also, they actually start predicting the next sentence in the corpus. So it's easy for them to create a training data and do it. That's the idea. Okay. So these pre-trained models are available. Then we can take it and start fine-tuning it with a little amount of data, only the little bit of adjustments with less number of data, and then we can just start using it. So that's the idea. So we'll do a quick, how are you doing on timing? Let's do a quick, a simple, before I do that, I want to show you one more, this exercise, sort of hugging face. So Hugging Face, what they have done is they got a lot of pre-trained models, a lot of examples and everything, their website, which tells you how to actually download their package, the Transformers package, and set up a pipeline and do things like question and answering task, text classification, language translation, all those kind of things you can wonderfully do using Python and PyTorch, and even TensorFlow also you can do it. So make sure that you get into this website and take a quick tour and other things. It's pretty useful. Okay. All right. So let's do an exercise here. I took some of those exercises, most of them borrowed from this place. You can go and take a look at it. Let's go here. Click on this link. If you have the PDF document, just click on this link. It should open up a Google Colab notebook for you. Okay. Are you guys there? Okay, I'm assuming you guys are following me. Just execute this these cells just by clicking this arrow, right? Oh, before you do that, I forgot something. Just go to runtime and make sure that you set it up to GPU, right? If it's set to none, make sure it's set up to GPU, and then save it. That's the first step. Again, go to runtime, change runtime type, and set the hardware accelerator to GPU. Save it. All right, let's start installing these packages by running this. Okay. Some packages are installed in the environment. We are importing the packages, Python packages. Some of them are they were just installed. So them get imported. Done. So we're all set to go. We're going to upload a database, load a data set for IMDb, which is movie comments, right? That's what we're doing. Done. So we'll just take a look at the data, what it is, right? It has got 3 keys, train, test, and unsupervised. And if you take a look at the train and test, it has got a data set, it's got a text and label. Text is the comments from the users of IMDb about a movie, and the label says it's a good movie or bad movie, right? 1 and 0. They got a training data set and test data set. And we want to just take a look at the first data point as a text. This is what it is, right? It's Bromwell High is a cartoon comedy. It ran at times. Looks like survive financially, blah, blah, blah. It looks like it's not a bad movie, right? This is what this comment says. Let's say what the label says. For that is 1. 1 means it's good. So that's how they created the training data. The training data is a bunch of paragraphs, and for every paragraph, it is either 0 or 1. Then the first thing what we need to do is, as I told you before, we need to convert these into numbers, right, for the computer. So we actually convert these, every word will be tokenized, which means it will be given a number, a dictionary kind of number, right? Bromel is 1, 2, those kind of things. It will be given a number, and every one of them will be having a predefined token if it is available from the pre-trained library, right? Or it will be initialized to a vector. That's important, right? So let's take a look at a tokenizer. Again, the transformer has provided an auto tokenizer because we are going to use a model from BERT. It will create a tokenizer which will work with BERT, right? Unless you have to do this separately for every model, right? This is called auto tokenizer, which is kind of cool. So it creates a tokenizer. And for example, if I pass a sentence to the exact tokenizer, that's what it does. It creates the, if you see this is what it done. It took hello, hello became 860,601. 101 is the start and 10202 is the end. And everything in between corresponds to every one of these words. Right? Hello, I think comma is this is one sentence, and the exclamation mark is 106, right? So it converts this into tokens, and every token will be given a word vector, right? So that it can, this is how the whole thing works. So what we are going to do is we're going to write a function which will take the data, what we have here, right? It's the text, text one, and it will convert that into tokenize it. And the data set has got a map function which kind of does the tokenization and maps it along with the labels, which is also available, and gives it nicely in a number format, right? That's what it's doing. You can just take it, use it, and I'm going to do the tokenization. So what, again, to step back and see what it is doing, it is taking all the sentences, right? 1, 2, 3, all these sentences, going through one by one. It's tokenizing all the words here, and it's also associating the label. Label is one for that. So you got a bunch of numbers, then the label. Now the text is gone at this point, right? That's what it's doing. It's creating the tokenized data sets. Again, in terms of code perspective, you're not doing a lot. Everything is all given to you, right? You can just keep doing it as I'm going around this loan book, right? So now you see that, and the tokenized data set right now, it has got the attention mark, input IDs, and the type token type IDs. These three were actually were the output of the tokenization. The label was already there. You just associate the right labels to the right tokens, and the text is whatever text was there before, right? That's everything, which is kind of cool. So if you see, the label is one, and if you see the input IDs, I just took only 10 of them because there are a lot. This is the starting word, and all these words represent here, like these words, right? And there are plenty of them. It's not, I just took the first 10. That's all I do. So we got everything in a format like training data set, like data with tokens. Tokens will be associated with embeddings, and the labels format we have got. Now, since we have a lot of data, we're going to create some smaller version of the data set. Also, we have a full training data set. Smaller versions will have only 100,000 data, and it's a randomized selection. And the evaluation data set will take another 1,000 data set, right? Instead of 25,000. Now we go for the training pipeline setup. The model is coming from, we're taking the bird-cased model, which is a pre-trained model. They're trained with all kinds of things. Then we also create the training arguments, the test trainer, we are using that. And we are using, this is the pipeline. This is the model, this is the training arguments, this is the training data set, this is the evaluation data set, right? This, we set up everything. It's downloading the model, actually, pre-trained model. Cool. We're all set at this point. We got the data ready. We got the model downloaded. Now we're going to train it. This is called fine tuning. Now we are training using IMDb data, our data, this 1,000 data points, right? That's what we're doing. So this will take around 3 minutes. Oh, sorry. This will take around 4 minutes. Let me runtime interrupted execution. I'll make it. Never mind. I'll just run it. That's okay. Let's take 4.5 minutes. While it's doing it, and then after that, it's going to compute. You want to compute evaluate the model and provide the results. That's what it's going to do, right? So while it's doing that, let me explain what the next steps are, depending on how much time is available. I also have an exercise for you, right? Last time we took data from the data sets, which we imported the data, the IMDb movie comments data. This time there is a database. The data we are going to upload is the quora.csv. From a CSV file, you can do the same thing, right? That's an exercise for you. We can do it together, but you can do it on your own. I got the database, the CSV file like this. The reason I'm giving you this is you can quickly, these are only 4 or 5 steps. You can have a classification model up and running once if you have a CSV file ready for you. Okay, let's take a look at the CSV file, how it looks like. This is the CSV file, right? While it's running, let's take a look at it. Oh God, this is okay. I don't know all these things. Okay, all right. So the CSV file has two data points. This is the text, which is a Quora comments, and here this says whether it's a sincere or insincere comment, right? And it's a label 0 means it's sincere, 1 means insincere, because people in that Quora.com, they want to make sure people are asking unnecessary questions. If they're asking mischievous questions, you probably throw it out, right? That's what they're trying to do. It's a sincere question. How many Quebec nationalists see their province as a nation in 1960s? It's a sincere question, right? Here, has the United States become the largest dictatorship in the world? It doesn't look like it's a sincere question, it's an insincere question, so it's marked as 1. This is the training data they created, right? If you see, there are a lot of sincere ones, there are insincere ones too, right? These are all mischievous questions, you can see it, okay? So this is the idea. So you can create your own data here. This can be any classification, right? You want to have sentiment analysis, or you want to create some kind of categorize the data into some kind of a label, right? Is this email, is it a useful email, or this should go to be escalated, this has to be escalated, right? You can make that as a 1 or 0, or you can have more than one label, multi-classification problem. You can set up all those data. So once you have it, this is very straightforward, right? Is this over yet? It's still going on. Another 2.5 minutes. So once you have it, you create this custom data set using this, and you have the custom data. And after that, you just follow the same process what I did before, which is creating the tokenization. You can copy the code from above, create a small training and eval data sets, is similar thing what we did before. And you download the model, set up the pipeline, include the code for creating the training pipeline. Again, you can copy it from above, train it, and you can evaluate the model, and you can try some predictions. Everything is given here, right? It's like 10-15 lines of code. You don't have to do anything apart from creating this wonderful CSV file. Okay, that's all you need to do, and try it out. And I don't know how much more time do we have.
Actually, it's maybe 2, 3, 4 more minutes.
Okay. So probably we'll be done with this, and I'll let the participants do the exercise on their own. Okay.
Yeah. We will send them your exercises, your Colab, and I think everybody could try by themselves.
It's a very self-explanatory. You can just try it. We'll just see the results for now, and we should be good.
Right.
It's almost done. Any questions for me?
I do not see any questions in Telegram group and on broadcast link. Does anybody have questions for Ravi? I think no. I think everything is clear.
Good. All right. Ask me any questions you want. The worst thing I'm going to say is I don't know, right? It's okay, right? So 30 more seconds will be done. Is everybody doing this as we are doing this? I hope you don't have any access issues with Colab. So
yeah, it's pretty simple. I think a lot of people doing it either in Jupyter Notebook or in Colab.
Yep.
I have an experience with both tools.
Yeah, this has made our life easy. I used to do this exercise using AWS and other things. It was a pain. Now it's so easy. And it's free too. Okay, so this is done. And the accuracy measurements, the training is running at this point. It'll be done another 30 seconds. Sorry, the evaluation is being done. I think we'll get around 86% efficient accuracy, I think. Which is not bad for 1,000 data points, right? So if you have more data points, you'll get better accuracy and more epochs.
Yeah.
Okay, all right, we're almost done. Yeah, oh, 61%. No, 87%. That's accuracy. And you can try this exercise yourself. It's very straightforward. And if you have any questions, feel free to reach me. And if you are in US, we are hiring. If you're interested being an NLP or a vision data scientist, feel free to reach me. So.
Okay, great. You could, by the way, you could send your location. You could send your who are you hiring to me, and I will send to our database of our participants, and if anybody is interested.
Do you want the profile, right? That's what you want. Job description.
Yeah, like description. Who are you hiring? Yeah.
Sure, I will send it to you. I'll do that.
Right. And I will send this notebook to everybody to let them try.
Yeah. The PDF document has the links and it's all set up to run. No issues. All right. Is there any other questions for me before we close?
I do not see any question. Maybe I have one small question. What is the best practice now is for sentiment analysis in NLP?
Sentiment analysis is nothing but the text classification. The kind of the model which we went through right now, it is an example of a sentiment analysis, right? It's either LSTM based or a transformer based, or even a bag of words based classification, right? That's what we use for sentiment analysis. And it's very sentiment analysis is one use case for text classification.
Mm-hmm. Maybe,
and you can use multiple models. You can start very, very simple, like a bag of words based model with the TF-ID, those kind of things you can do. And then you can move on to deep learning, which is RNN or LSTM models. Then if you're not satisfied with that, you can use XLNet and BERT. Of all the models I've seen, XLNet probably produces the best results.
Right.
But it's not consistent. You can't just blindly say XLNet produces great results. Sometimes bag of words, LSTM do a very good job. So